Aren't these pretty pictures? This is a snowflake. That's ice. Nobody sculpted that. That forms in the sky all by itself.
I've heard that before, yeah.
It's so cool. And they're always six-sided, snowflakes are. I grew up in Minnesota and Iowa, played out in the snow a lot, so I looked at a lot of snowflakes when I was a kid. And they are all different. I mean, it's mind-boggling.
I think there's got to be at least one or two that are the same.
You would think, wouldn't you, that there must be at least two that are the same somewhere. But good luck finding them. You know, I can't really disprove that idea. Here's another crystal. I think this is quartz and gold. These are examples of crystalline solids. Question or stretching?
Question.
Okay.
Snowflakes, you said they're always six-sided. Is there a reason why they're always six-sided?
There is a reason why.
Does it have something to do with the electrons?
It has to do with the crystal structure that water takes on when it freezes. Water forms a crystalline structure based on its geometry and the interaction of its intermolecular forces, and it's a hexagon. So for crystalline solids, we sometimes see these just breathtaking geometric shapes. This one reminds me of Superman's lair up by the North Pole, with all the crystals sticking out. But the results of these geometric shapes that we see, those are the result of the patterns within the atoms and the molecules. So how do people figure out how the atoms and molecules are arranged in a crystal? They used a technique called X-ray crystallography. So we've learned about electromagnetic radiation and waves and how we can get constructive or destructive interference. If you take two waves that are in phase, their peaks are lined up and their troughs are lined up, they will constructively interfere and the amplitude of the wave gets larger. If they are offset, if they are out of phase, they will cancel each other out. And we saw an example in that video of the guy with the box, right? And he had the diffraction pattern and the light spots and the dark spots. So if we have light passing through two slits where the distance between the slits is similar to the wavelength, then we get this diffraction interference pattern caused by alternating constructive and destructive interference. So we can use that idea to determine the spacing between atoms within a crystalline solid. So in the crystals, the spacings of the atoms are on the order of 10 to the 2, or 100 picometers. And that corresponds to the wavelength of X-rays. X-rays are electromagnetic radiation. They just have a shorter wavelength, and so they're higher in energy. But they can also cause interference patterns. So when we have the X-ray interact with a crystalline lattice, my stylus is dying here. I keep pushing on it too hard and it's flat now. When it interacts with that crystalline lattice, we can get a diffraction pattern, and that diffraction pattern is related to the spacings between the planes of the atoms. So here you have your crystalline solid, you take an X-ray source, and you get a nice beam of X-rays, and you shine it on this crystalline solid, and you get a diffraction pattern. And the diffraction pattern arises from how the different atoms or molecules are spaced within the crystal. So here is an illustration. Here we have some atoms. Okay, I'm just going to use my finger. Here we have some atoms, little balls, right? And here we have two layers. So these are called atomic planes. And we have X-rays. These two X-rays are coming in parallel to each other, and they are in phase. And as they hit this solid, ray 1 bounces off of this atom and is reflected. Ray 2 goes through the first layer and bounces off the second layer and is deflected. If the two waves here are still in phase, then they will constructively interfere and cause a bright spot. If they are out of phase, they will destructively interfere, and there'll be a dark spot. The difference that ray 2 travels, the difference in its path length, is 2a. So A is the distance here, and there's an angle theta. So we're shining the radiation at an angle theta above the plane of the surface, and the distance that ray 2 travels is A plus A, 2A. And that is related to theta. So the sine of theta is A over D. This is geometry, and if you don't remember that, that's fine. So A equals D sine of theta, and so we come up with what's known as Bragg's law. N, which is an integer, times theta, the wavelength of the radiation, is equal to 2 times D times the sine of theta. D is the distance between the two atomic planes. Okay, and so what we'll do is we'll shine the radiation at different wavelengths until we find a wavelength where it produces a maximum intensity. So we maximize the intensity by constructive interference. Any questions?
How does it go through the first layer?
It goes through the first layer because X-rays can go through things.
How do they make it not go through something?
Well, you know, in this illustration, they're saying it's bouncing off the edge of this, what looks like a marble, right? I don't think it's really going to bounce off the edge of the atom. It's probably going to bounce off more like the nucleus. But that makes for an ugly picture.
Gotcha. So
But, I mean, there are solid things inside the atom, right? The nucleus is very, very dense. So if you hit the nucleus, it's definitely going to be deflected off.
so one goes and hits the nucleus, and the other one goes through the outer
Yeah.
shell and then hits
It'd probably be more accurate to have this point of reflection be here in the nucleus. Yeah.
Is it kind of like snail's law?
Snail's law?
I'm sorry, it's different. Yeah.
Yeah, I don't remember all the names of the laws from physics. But this is definitely related to physics and geometry. You know, angles of reflection and those sorts of things with optics. So typically what we do is you look for the angle that produces maximum constructive interference, and you measure that. And then you can calculate the distance between the atomic layers is an integer times the wavelength of the X-rays over 2 times the sine of theta. So theta is what you're measuring. X-ray crystallography has been used to determine the structure of all kinds of things, and it was very important in finally determining that double helix structure of DNA. It was really important in that. So let's do a problem. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. Well, n lambda equals d sine of theta, right? So this 157 picometers, what does that correspond to? Well, 157 picometers, what letter in this formula does that correspond to? That would be D. D is the spacing between the two layers of atoms. So D equals 157 picometers. 154 picometers, what's that?
That's the wavelength.
That's the wavelength, lambda. The wavelength of the radiation. So 154 picometers. It's kind of an ugly 4. I'm writing with my finger today. And it says that n equals 1. So we want to find what theta is. So let's rearrange this a little bit. Sine of theta is going to equal n lambda over d. So that's 1 times 154 picometers divided by 157 picometers. Picometers cancel out. We don't need to convert them to meters because they're just going to cancel out.
Wait, what about the 2?
The 2. I forgot the 2. Thank you. There's a 2 in there. N lambda equals 2 d sine theta. So 2, and there's the 2. There we go. That's better. Thank you. So 2 times 154 divided by 157.
Yeah.
Oh, just shoot me now.
We'll get there eventually.
We'll get there eventually.
It's a work in progress.
Everybody makes mistakes.
I've made sorry, I said it earlier.
Okay. I think that's right now, yeah?
I believe so.
So I have 154 divided by 157, divided by 2. 0.49 044 586. Now, it might be tempting to round that to half. Don't round stuff. It's better to carry extra digits. You can always cut them off later, but if you round stuff in the middle, you sometimes end up with the wrong answer. So that equals sine of theta. How do we find out what theta is? We need the inverse sine of the 0.49. I use this so rarely that I'm... And answer... Nope, that was the wrong one. There we go. One nine zero four four 586. We're trying to find some theta. So 29. And this is where, you know, using sine, okay, we haven't covered that in terms of significant figures. This is where we should just try to use a reasonable number, right? So we've got wavelengths that are 3 significant figures, and so calling this 29.4 degrees is probably reasonable. Any questions? We'll save that for another day.